Yeah, so it's great to see everyone. I feel like I haven't seen a lot of people from the broader community outside of Stanford for a while. So today I'm going to be talking about learning exploration strategies via meta-reinforcement learning. And before I start, kind of a quick disclaimer is that the problem that I'll be talking about is in many ways quite different from the classic exploration problem, but hopefully that will also make it potentially also kind of an interesting new thing to be thinking about. So first is some motivation. I like to think about why humans are good at reinforcement learning. If we think about how humans might want to learn how to play a new card game, or learn how to use a coffee machine, or learn how to kind of figure out how to manipulate objects to pack a dishwasher, or play a game like this where you need to balance different game pieces, humans are really good at learning these kinds of things. They can probably learn them a lot faster than most reinforcement learning systems that we have now. And the reason why humans, I think, are really good at learning these kinds of things is that people have previous experience. We've already built up a representation of the world that facilitates exploration and learning of these tasks. We may have learned other card games, we've maybe used other coffee machines or manipulated dishes before, so that we can have a reasonable idea for how to figure out how to solve these tasks. Whereas in contrast, our reinforcement learning agents start tabula rasa. They don't have any previous experience. We're starting them completely from scratch, from a clean slate. And while this has a lot of benefits because you don't have to build any knowledge into the system itself, it also means that these systems aren't leveraging any previous experience that they had. And this may be analogous to trying to have a baby start from scratch for solving all sorts of tasks that we may want to do. And so what I'd like to talk a bit about today is how we might allow reinforcement learning agents to leverage previous experience when they're solving new tasks. And this will be especially relevant in situations where we may want the reinforcement learning agent not to learn one single task, but to learn many different tasks. And of course, this is motivated also by a lot of the work that I've done in robotics, where ultimately we don't want a robot just to do one very narrow thing for us. We'd like that robot to be broadly useful. Now, as a second piece of motivation, I think that a lot of times when we think about exploration, we try to build general purpose algorithms that will work for a wide variety of domains. And in many ways, we think about using the same exploration algorithm for a wider range of reinforcement learning problems, ranging from navigating an environment, to making recommendations to users, to learning a policy for computer system caching, to learning to physically operate a new tool or machine. And it doesn't quite make sense, to me at least, to use the same exploration algorithm for these different kinds of problems, especially if you have a means to latch on to the particular structure of a particular domain, such as manipulating objects. If you know that manipulating objects leads to certain outcomes, or trying to explore an environment in such a way that may allow you to navigate towards a goal. And in many ways, this is how we currently approach exploration, where we try to have a single algorithm for solving all of these tasks. Now, what I'm going to talk about today isn't going to completely sidestep this overarching exploration problem in reinforcement learning, but it's going to try to provide a tool that allows us to leverage experience from previous tasks to very quickly explore a new task. So in particular, what I want to talk about is if we can learn exploration strategies based on experience from other tasks in that domain, to try to learn a more domain-specific exploration strategy that can be even more efficient and more targeted towards that domain to explore much more efficiently. Okay, so the ideas that I'll talk about will build upon the idea of meta-reinforcement learning. So I'll first give a few slides on what meta-reinforcement learning is, and then I'll talk about some of the challenges with regard to exploration. So the goal of meta-reinforcement learning is as follows. We want to be able to collect a small amount of experience in a new Markov decision process from some exploration policy or some exploration strategy, and then using that experience, learn a policy that solves that MDP. So learn some procedure that can take as input the data that you've collected during exploration, and give you a policy that solves that task. So this is the goal. We want to be able to essentially do this at test time or at meta test time, where we want to be able to solve a new MDP. And the way that meta-reinforcement learning approaches this problem is you say, well, what if we had the ability to collect experience in other MDPs? The goal is to be able to learn how to efficiently explore and solve many training MDPs such that when you're given a new MDP, you can quickly explore it and solve it. And so essentially what we're going to be trying to do is to learn an exploration strategy and an exploitation strategy that will allow us to solve all of the MDPs in our set of meta training tasks. Now, one key assumption that all meta learning algorithms make is that the meta training and the meta testing MDPs should come from the same distribution over MDPs. And this assumption is important so that we can expect reasonable generalization to new MDPs at test time. Okay, so that's generally how the training setup looks like. We typically assume a set of training MDPs, and then we want to be able to generalize to a new MDP from that same distribution. A common approach that we'll focus on today for solving this problem is to implement the learning procedure using a recurrent neural network, using kind of a black box neural network. And what this looks like, it might be something like this, where you have this neural network. It takes as input states and rewards that it receives over time and produces the next action. And the exploration strategy and the exploitation strategy is built into this model. You might ask, well, okay, is this just a recurrent policy? Is this like not really anything different from that? And kind of the key difference is that the hidden state is going to be maintained across episodes within an MDP so that it can remember the experience that it has learned and also remember the rewards that it has received as passed in as input. And second, this recurrent network policy will be trained across a family of MDPs, potentially with varying dynamics and varying rewards. And it has to infer for a given MDP what is the strategy for solving that MDP, potentially implicitly learning something about the reward function and something about the dynamics. Okay, so that was a quick kind of primer on meta-reinforcement learning. Now, a subproblem of meta-reinforcement learning is trying to figure out how this policy or how this meta policy should explore the environment when faced with a new MDP. So the really kind of vanilla approach to solving this problem is just to optimize for exploration and exploitation end to end with respect to reward, or potentially more specifically with respect to your kind of overall regret. And this is really kind of the widespread approach that's used by most meta-reinforcement learning algorithms. You're essentially just optimizing that big recurrent neural network such that it leads to kind of large cumulative reward. And this is nice in that it's very simple. We just have to train it with regard to this kind of final objective. It also in principle will lead to the optimal exploration and exploitation strategy, assuming that your recurrent network has enough capacity and you're able to actually optimize that. But in practice, and also actually in theory, there's actually a really challenging optimization when you're faced with a hard exploration problem. Now, why is this the case? Why is it really hard to learn how to explore? To explain this, let's look at an example. So one example meta-reinforcement learning problem might look like as follows. Say we want a robot to be able to learn cooking tasks in a new kitchen. And so what we do is we train it across a lot of different kinds of kitchens to learn many different kinds of tasks. And then after learning in all these kitchens, we want to deploy the robot in our own kitchen and have it be able to quickly learn to cook different things for us in our own kitchen. So this is an example potentially of a meta-reinforcement learning problem where we learn how to learn in all of the training kitchens and then try to transfer to the new kitchen at test time. So this is a pretty challenging exploration problem because if you're in a new kitchen, you need to figure out where all the ingredients are, where all the tools are, and so forth. And so you may need to explore lots of different things. Now, why might it be hard to learn exploration strategies that are effective in this type of situation? So the end-to-end approach is going to be optimizing for exploration and execution end-to-end to maximize reward. And you end up getting this chicken and egg problem where the execution or the exploitation, it needs to learn how to cook, and the exploration needs to learn how to find ingredients. And both of these rely on each other. So if you don't know how to find an ingredient, if you have a bad exploration strategy, then it's going to be hard to learn how to cook because you don't have enough information to solve the task. And likewise, if you haven't yet learned how to cook, then that's going to give you very low reward for any exploration strategy that you may consider. So this is we have this sort of coupling problem, which is actually a pretty big problem in practice too, which is that learning the exploration and the execution depend on one another. And this leads to both potentially local optimum in the optimization landscape and or very poor sample complexity when you actually try to learn these end to end. Okay, so how might we try to address this challenge? First, I'll overview some recent approaches for addressing this, and then I'll talk about an approach that I think is a bit more satisfying. So one solution to addressing this chicken and egg problem is to leverage alternative exploration strategies when exploring each new MDP, rather than trying to optimize exploration end to end. So one example of this might look like trying to use posterior sampling or Thompson sampling when faced with a new task. So what this looks like is these approaches learn a distribution over a latent variable that captures the variation in your MDPs or your tasks. And they also learn a corresponding policy for each of those latent variables that will solve each of those tasks. And then once you learn this kind of latent task variable and the corresponding task policies, then you can sample from this distribution from your kind of current posterior over your task distribution, and then sample from the corresponding policy. So this basically exactly corresponds to Thompson sampling, except that we're doing it in this latent space over the kind of distribution over tasks that we, over the tasks in our meta training set, or over the tasks that we, or if we've ruled something out, over the kind of smaller set of posterior distribution. So for example, if we have a task distribution where the goal is to navigate to one of these circles, and you only get a sparse reward when you're inside the circle. So each of these lighter circles correspond to different tasks in the task distribution, and the dark circle corresponds to the current task. Now what this will look like is first you sample from your prior over your latent variable and get trajectories that look like this. Then you update your distribution over over the latent task distribution, which we'll denote with this Q phi, and then you explore new directions with the policies for those tasks, and then eventually you do find a trajectory that starts receiving reward, and then you start exploiting that because your posterior is now kind of zoned in on the correct task. So this works pretty well in a range of situations, but there are also situations where posterior sampling might not work well. So for example, if the goals are really far away and maybe there's a sign on the wall that tells you what the correct goal is, then posterior sampling isn't going to look at the sign, it's still going to attempt the task. This may be arbitrarily inefficient as the goals get further and further away. Okay, so there are a couple of other approaches also, other alternative exploration strategies beyond posterior sampling. So we could use intrinsic rewards in the inner loop to explore, and this was done by this paper here. We could also try to explore in a way that recovers the task dynamics or the task reward. And the way that this works is you train a model conditioned on the data that you've collected so far, and then you try to collect data so that this model is accurate. And this can overcome some of the challenges of posterior sampling in some cases and actually lead to an exploration policy that's much more efficient, that takes a strategy that looks like this. But of course, there are also situations where this won't work well. For example, if you have lots of distractors or a very complex high-dimensional state space, then learning this model may be very challenging, and your exploration policy may try to focus on distractors that vary across the tasks and not actually task-relevant information. So essentially, these are kind of a collection of more heuristic approaches that are fairly principled, but may be inefficient when learning to explore. So the upside is that these approaches are very easy to optimize because they, in some ways, decouple the exploration problem in the inner loop from the outer meta optimization. And many of them are based on principled strategies, but they can be suboptimal by arbitrarily large amounts in some environments. Okay, so with this kind of overview of how meta-learning algorithms learn how to explore, what we want to try to solve is trying to figure out if we can avoid this chicken and egg problem without sacrificing optimality of our learned exploration strategies. And the answer to this question is yes, we can actually do this. And I'll next talk about some work that was done by my student Evan that was trying to solve this problem. And the key idea of this approach is that we're going to try to decouple the exploration and the exploitation by acquiring a representation of task relevant information. So the way that this works is in the meta training process, we have a set of MDPs that we want to learn how to explore and solve. And first, we learn a policy that can execute each of the tasks and simultaneously identify key information about those tasks. So the way that this works is we have some identifier of the MDP that may be a one-hot vector or maybe slightly more descriptive, and we learn an execution policy that can solve each of our training MDPs conditioned on this MDP identifier. Further, we also bottleneck the representation of the MDP identifier to encourage it to throw away information in that identifier that isn't actually relevant for solving the task. For example, changing the wall color, things about the wall color and the decorations are not relevant for actually solving the task. Then we learn how to explore by trying to recover that task relevant information. And the way that we do that is we train an exploration policy so that it's able to predict this bottleneck representation that captures task relevant information. And then once we do these two steps, we can then run our exploration policy. This produces an exploration episode from which we're able to predict the task relevant information, which we then pass to the execution policy. Okay, so what are the properties of this approach? So theoretically, we try to look at both the performance as well as the sample efficiency of this algorithm. And first, we can show that the objective of this approach is consistent with the end-to-end optimization under fairly mild assumptions. And this is really exciting because this means that we can in principle recover the optimal exploration strategy, unlike the other approaches that I was talking about where you use things like posterior sampling or other strategies. And then the second result, we were trying to look at the sample efficiency of this algorithm. And this is a lot harder to analyze. So we looked at a very simple bandit-like setting with A arms. And what it looked like is in each of the MDPs, MDP I, one of the arms yielded a reward, and this arm varied across the MDPs. Further, in all of these MDPs, one of the arms deterministically revealed which of the arms is the rewarding arm. So the optimal exploration strategy is to look at arm 0, which will tell you which arm is the best one, and then to pull arm I for that MDP. And we can show that in this very simple distribution over MDPs, the end-to-end approach requires at least A squared log A samples for meta optimization, whereas the dream algorithm requires at most A log A samples for the meta optimization if you assume Q-learning with a uniform outer loop exploration strategy. And so kind of graphically, this looks like this, where the dashed line is showing the theoretical result and the solid line is showing the empirical result if you actually run on this bandit-like setting. So you see a pretty huge difference in the efficiency of these two algorithms. So kind of the takeaway is that DREAM allows us both to recover the optimal exploration strategy while also being considerably more efficient to meta learn. I'm a little bit low on time, but empirically this also works quite well. So we looked at a setting where we want to be able to look at a sign and use that to determine what the task is. So the agent will go first, look at the sign, realize that it should go to the blue objects, and then use that during execution to successfully go to the correct object. And we see this performs much better than the existing state-of-the-art MetaReinforcement Learning algorithms as well. Cool, so to leave enough time for discussion, I'll kind of end it there, and I'd be happy to take some questions. Thank you.
Thanks, Chelsea. This is really interesting approach to exploration from a meta-learning perspective. Now we have some time for questions from the audience. and panelists.
So just a quick clarification question. If I think about the reinforcement learning setting instead of meta-reinforcement learning, then certainly there's been a lot of recent work about basically doing exploration in the latent representation that the agent is learning, both empirically and theoretically. And is this, should I think of this as something in similar space, or is there a bigger difference?
Yeah, that's a good question. So I think that one thing that's pretty different that we can kind of use when we're actually like analyzing this is the fact that we know that we're looking at a distribution over MDPs, and essentially I guess you can view it as when you have a distribution over MDPs, you're trying to identify what's different about those MDPs. And once you identify what's different about those MDPs, then you're basically done. That means that you've kind of solved the inner loop exploration problem. You figured out which MDP that you're in, and then after that, you just need to actually have solved that individual MDP. So because of this kind of additional structure of the kind of meta-RL problem, this allows us to kind of derive this algorithm that that kind of leverages that structure to work better. Does that answer your question?
Yeah.
Hi, Chelsea. Great talk. Another question, I mean, in general about meta-RL, right? So, let's say I have the base, like lower level reinforcement learning problem has a horizon like H, or like 1/1 gamma, something like that, right? But if I think about the horizon of the meta-RL algorithm, the horizon here is actually correspond to the sample complexity of like solving and exploring each lower level problem. And this is like similar, I guess, you have a similar realization back to this old, Bayesian adaptive MDP setting. I think in spirit is kind of like a different instantiation of like the meta-RL algorithm. And the difficulty we had like back then was, the meta horizon is simply just like too long to efficiently optimize. How do you think of this difficulty? And or I guess in what circumstances do we expect that we can get around it?
Yeah, so I think it really depends on how hard the exploration problem is, and I guess also how broad your distribution of tasks is. So basically the horizon of the optimal like meta policy is going to be the time it takes to explore plus the time it takes to actually like perform that task. And if the exploration phase is, well, that's potentially going to be dominated by the exploration phase because the horizon to solve the task is just kind of the horizon of a normal MDP. And the length of that exploration phase is basically just going to be how long it takes to identify which task you're in. And so if you have an extremely broad task distribution with a lot of tasks, it's going to take it's going to take more data to figure out which of those tasks that you're in. And if you have a very narrow task distribution, like if you have just like 2 tasks, for example, then you just have to find the one thing that kind of distinguishes between the two MVPs. In general, I think that it's actually, like for most meta-RL problems that we care about, I think it's actually quite reasonable because like figuring out like discerning information about an MDP in your task distribution is usually not that hard. For example, I guess if maybe you have one situation that we looked at is we have a robot, the robot is on different terrains. You just need to kind of probe the environment to find which terrain you're on. And then once you kind of figure out what terrain you're on, then you're done exploring and you should just exploit that. If you're in a setting where maybe you're a recommendation system and you want to explore for different users, you essentially need to probe the user until you figure out kind of the sufficient statistics of that user that allows you to make effective recommendations for that user. So I think that basically the narrower your domain is, the easier it is for exploration to be able to identify the sufficient statistics of each of the MDP. And I think that this will be considerably better than than basically tabula rasa exploration, because you're not starting from scratch. You have kind of domain-specific knowledge that's built into your MetaRL algorithm.
I had a question, if I can sneak in before the time runs out. So one thing that seems pretty significant in your ability to sort of like efficiently explore new tasks in the MetaRL setting is that this idea that the tasks sort of have like some sort of shared information, so that like you can sort of like leverage that. Is there a way of quantifying that to have that play into like sort of exploration hardness results or like generalization bounds?
Yeah, so it's basically, it seems like your question is like, can we quantify the complexity of the task distribution, essentially?
Yeah, so basically, like, can you quantify sort of how much shared information there is between the tasks?
Yeah, so in the, I guess, so if you have n tasks, then you know that you need log n bits to kind of represent the differences between those tasks in the, well, by kind of coding theory. So that's kind of one thing. If you have an infinite space of tasks, which I think is kind of the more interesting setting, then it's I guess it's harder, but I guess if some tasks share, if their optimal policy is very similar, then then you'd expect it to be kind of more compressible. I haven't seen any works that really study this. It certainly seems interesting. And I guess one thing I will mention is that if you have a completely random set of tasks, then MetaRL isn't going to buy you anything, because it needs to be able to pick up on that shared structure to learn more efficiently. If you have literally a uniform distribution over tasks, then there's no shared structure and there's nothing that you can use to more efficiently explore. Luckily, in the real world, there are many things that have common structure, like physics, the laws of physics, and things that are desirable in general. But yeah, I don't know of any works that have kind of specifically looked at this problem of doing it, but I would imagine that, well, so it's certainly something that we can empirically do. Analytically, I think it's messy, because distribution over MDPs may not even, like, MDPs may not even vary parametrically. Although perhaps by analyzing the optimal policies for each of the MDPs in your distribution, you may be able to think about things more analytically.
Cool, thanks.
Chelsea, I know that this work is it's really interesting, and it's really cool to see it scales really well too. One question I wondered about for the bandit results is Li Hong and I sort of a while ago, back in 2013, thought some about when there was sort of a finite set of tasks for the tabular setting. And I was curious whether or not there might be, so in that setting, we were thinking of there being like a finite set of different types of MDPs, and you'd continuously be sampling from them. So you could learn the latent distribution, and then you could leverage that as sort of a classification problem later, and that reduced the sample complexity. I wasn't sure in your case whether the new tasks are always distinct from all the prior tasks, or whether you might get repeated tasks, in which case, even if there isn't structure among the tasks, you could still improve learning because you would have already seen that and you could identify quickly you've already seen it.
Yeah, so for this specific result, it depends on the number of arms in the bandit. And so I guess this is assuming that if you have at least kind of A arms, or you have A arms and at least A MDPs, then this is what the result would look like. If you have more than A MDPs but still A arms, then the complexity of results don't change. So even if you have redundant tasks, then you still get the same result, which is nice.
Cool.
Okay. We have maybe 1 minute for one last quick question.
I'm going to jump in then. Great talk, Chelsea. This is fantastic. And regarding the MetaRL setting, and in exploration, there's typically these pathological examples that show the importance of a certain approach or a certain technique. I'm wondering, have you thought about, or do you have pathological examples for this case as well, saying if you don't have MetaRL, if you don't take the MetaRL perspective, you're going to fail here?
So you're saying, sorry, to clarify, you mean pathological examples for this MetaRL algorithm, or pathological examples where MetaRL overcomes?
The latter.
latter. Well, so like if the tasks themselves, like if you can't figure out how to solve the individual tasks, then like MetaRL isn't going to help you. One of the kind of subroutines of this method was basically to learn a policy for each of the tasks in your task distribution conditioned on some representation of that task. So in some ways, it doesn't really do anything to sidestep that challenge. What it does allow you to do is once you have solved those tasks, you can kind of pretty efficiently learn how to solve new tasks from that task distribution. And so perhaps one thing that it does get around is that if you're trying to solve that new test task from scratch, then that may be like pathologically difficult. Whereas MetaRL kind of leverages this previous set of tasks, and maybe some of those previous set of tasks have more shaped rewards that allow you to kind of bootstrap exploration off of, that allow you to actually be able to tractably solve this new test task. Whereas if you're trying to solve that test task from scratch, you may have had no hope. So that's kind of where I see it potentially kind of contributing to the broader classical exploration problem.
Thank you.
Okay, thanks, Chelsea again. And now let's move to the